For more physics-related videos, please subscribe. Welcome to Stellar Physics 4C. In this video, I'm going to go over the thermodynamics of degenerate matter. Stellar core remnants are made up of degenerate matter, so if we want to understand the physics of objects like white dwarfs and neutron stars, we have to understand what degenerate matter is. I actually already briefly covered degenerate matter in Stellar Physics 2A and 2B, but in this video I'm going to go over it in more detail because degenerate matter is a state of matter we are not accustomed to as human beings. I've rated the physics level in this video as advanced. This is mostly because thermodynamics is difficult. In my opinion, it's the most difficult part of all physics. And degenerate matter is very non-intuitive because we're not accustomed to it. But as you're going to see, if we take it step by step, it's not that bad. First, let's go over the relationship between temperature and occupation probability. In Stellar Physics 2A, we derive this expression for the number density of a given particle species. So little n is the number density, g is called the degeneracy, and what it's doing is it's counting how many particles can be in a given momentum state, or energy state. They're interchangeable using this expression right here. So p is the momentum, and that's what we're integrating over. E is the energy associated to that momentum. Phi is the chemical potential, which is the energy required to add one particle to the system while keeping the entropy constant. And T is the temperature. Now, if you watch chapter 2 of this series, you'll know that for fermions, this is a plus, and for bosons, it's a minus. I'm only going to do this for fermions because degenerate bosons are not really relevant for stellar physics. Degenerate bosons are very interesting and lead to something called bose-einstein condensate, but that's a whole different topic altogether, and we're not going to cover that. Now, this factor in the denominator here represents the occupation probability. That is, the probability that a particle will be in a given momentum state. For fermions, what you have to keep in mind is that two fermions cannot share the same overall state. So if a state is occupied and you want to add another fermion, you have to put it in a different state. You're going to see what I mean here in a little bit. Now, what happens to this occupation probability if the temperature is 0? Well, if the energy is less than the chemical potential, then the exponent will be negative, and if t equals 0, it will be negative infinity, and e to the negative infinity is 0. So the occupation probability will go to 1, meaning that energy state has a 100% probability of being occupied. If, on the other hand, the energy is greater than the chemical potential, then the exponent will be positive, and as t goes to 0, you'll go to positive infinity, and e to the positive infinity is infinity. Now this is the denominator of the occupation probability, so 1 over infinity is 0, so the probability of a state being occupied in this case will be 0. This is what we mean when we say we have a degenerate probability distribution. This term degenerate probability comes from mathematics, and it refers to a probability distribution in which all states either have a probability of 1 or 0. So there's no probabilities of 0.5 or 0.7 or something like that. So for example, if you flip a coin, you have a 50-50 chance of getting heads or tails. That's not a degenerate probability. If on the other hand you have a two-headed coin, where both sides are heads, then your probability of getting heads is 1, and your probability of getting tails is 0. That would be a degenerate probability distribution. In the case of degenerate matter, the chemical potential is called the Fermi energy, and this is the energy of the highest occupied state at 0 temperature. Right? So this is the energy where if you go above it, the probability will be 0, and below it, the probability will be 1. Let's try to visualize what's going on here. Imagine you have an energy bin, and that bin is filled up with possible energy states. So if you add a particle to this bin, it could fill any of those energy states. And in the case of degenerate matter, I'm going to fill these energy states up at the lowest energy possible each time. So the first particle will go in the lowest allowed energy state. The next one can't occupy the lowest energy state because fermions can't occupy the same state, so it will have to go to the energy state above it. The next particle after that will have to go into the energy state above that, and so on, until you've run out of particles and you've filled up some number of energy states with those particles. So here the blue states are occupied and the yellow states are unoccupied. And this was what we define as 0 temperature. The highest occupied energy state will be the Fermi energy. Now, in reality, you can put more than one particle in here. That's what this factor G is. This tells you how many particles you can put in a given energy state. So, for example, G might account for magnetic moment. So all particles have a magnetic moment. They're like little magnets. And that magnet can be pointing up or down. And that corresponds to two different states. So in this example, the degeneracy would be 2. So in each energy state down here, I could put 2 fermions. One with its magnetic moment pointing up, and one with its magnetic moment pointing down. This is just an example. The degeneracy doesn't have to be 2. It could be any positive integer in principle. So hopefully this little cartoon helps you visualize what's going on. So now, in the zero temperature limit, the number density reduces to an integral from 0 to the Fermi momentum, where the occupation probability is just 1. We don't have to integrate any further than that because the occupation probability after the Fermi momentum will be 0. The Fermi momentum is related to the Fermi energy via this standard energy momentum relationship. This state of matter is pushing the limits of quantum mechanics, and specifically of the Heisenberg uncertainty principle, which states that your uncertainty in position and your uncertainty in momentum have to be greater than about h bar. Now in this case, they're going to be very close to h bar because we're going to be right at that limit. Basically what it means is your particles are as crunched together as they can possibly be. And the reason the number density has this form of integrating over the momentum is because we have a relationship between the wavelength of a particle and its momentum, given to us by this physicist whose name nobody can pronounce. In English, he's typically called de Broglie or de Broglie. It's a French name, and it's actually pronounced de Broglie. But actually, it's originally an Italian name, which I believe in Italian will be pronounced something like de Broglie. Either way, he pronounced it de Broglie, and he tells us that the wavelength times the momentum of a particle is a constant. If we interpret the wavelength as the space occupied in one dimension by a particle with momentum p, and convert that to 3 dimensions, so we can take in effect the wavelength cubed, which will be a differential volume, and then momentum is also a 3-dimensional vector, just like position, so we take a differential 3-dimensional momentum volume, so to speak, divided by 2 pi h bar cubed. This is cubed because this is 1-dimensional, and now we've gone in 3 dimensions. This should be approximately 1. Integrating over d3r will just give us the volume, which we've divided out because we have the number density. And then this d3p, if you're spherically symmetric, will be 4 pi p squared dp. So here we have the p squared dp, and then the 4 pi is how you get this factor over here. And then you have to multiply by g to account for the number of particles that can be in a given momentum state. So hopefully that explains where this expression for the number density comes from. At this point, your brain may be hurting a little bit, so let's try to visualize the difference between degenerate and non-degenerate matter. If I draw a graph of the probability versus the energy state, so the probability being the probability of occupying a given energy state, and here I have a probability of 1, and here I have the Fermi energy, at 0 temperature, the probability distribution will look like this. So below the Fermi energy, the probability of occupying a state is 1, and above, it's 0. And if we go back to our energy bin cartoon, here we have the Fermi energy, and every state will be filled up right up to the Fermi energy. So this is considered a fully degenerate system, 0 temperature. The chemical potential will be the Fermi energy. Remember what the chemical potential is. It represents the energy necessary to add a particle to the system while keeping the entropy constant. Now in this case, the entropy is 0. Why is that? So what does entropy measure? Sometimes it's said that it's a measure of disorder. I don't think this is a really good way of describing it, because who decides what's ordered and disordered? What it really is a measure of the number of ways you can arrange a system. And specifically, it's the log of the number of ways you can arrange a system. So in this case, how many ways are there to get this system? Well, there's only one. You just stack all the energy states one by one until you're out of particles. There's only one way to do it, and the log of 1 is 0, so the entropy is 0. And if you wanted to add one particle, while keeping the entropy zero, you'd have to stick it right above the Fermi energy, or right at the Fermi energy. And so the chemical potential is the Fermi energy, because that's the energy you got to put in the system to add one particle while keeping the entropy constant, or in this case, zero. Now, what if the temperature is not quite zero, but close to zero? In this case, the probability density will look like this. Most of the lower energy states will be occupied, and then as you get close to the Fermi energy, you'll have a few of them, a few states that may not be occupied, and a few above the Fermi energy that may be occupied. So this is a low temperature limit, and what we mean by low is that the temperature is much less than the Fermi energy. This is actually more realistic. It's actually physically impossible to get exactly zero temperature. So now our energy bin cartoon will look like this. Almost all of the lower energy states will be occupied, and then near the Fermi energy, you'll have some particles that have a little extra energy that are up here at slightly higher energies than the Fermi energy. So this system we still call degenerate because it's mostly degenerate. In this case, the chemical potential will be close to the Fermi energy. It'll actually be a little bit less because you can stick another particle slightly below the Fermi energy and not change the entropy. And now the entropy won't be exactly zero, it'll be very small, because these particles up here will have a little bit of entropy because there's going to be more than one way you can arrange them while maintaining the same system. As an analogy, I kind of think of this as like a glass of ice. If the ice is super cold, it will look like this. All of the molecules will be frozen in this glass of ice that's filled up to some height that corresponds to adding up all of the particles. If you increase the temperature a little bit, you'll get a few particles that might evaporate and might float around a little bit above the ice, and this will have a little higher entropy. Now, this is just an analogy for visualization purposes. Ice is not at all degenerate matter. Now let's see what happens if we have high temperature, meaning the temperature is much greater than the Fermi energy, or actually more accurately than the chemical potential. In this case, the probability distribution will look something like this. Almost all of the occupied states are well above the Fermi energy. An example of this would be an ideal Maxwell-Boltzmann gas. Now, if we take a look at the energy bin cartoon, it will be distributed like this. Almost all of the occupied energy states are well above the Fermi energy, and maybe you'll have a few stragglers down here a little bit below the Fermi energy, but for the most part, the Fermi energy won't really have anything to do with this system. In this case, this is called non-degenerate matter, because here none of the probabilities are 0 or 1. They're all somewhere in between. The chemical potential will be pretty much unrelated to the Fermi energy, and the entropy will be much greater than 1 because there will be a large number of arrangements that will lead to the same state. So hopefully this clears up the difference between degenerate matter and non-degenerate matter. If you're finding this video interesting so far, be sure to like and subscribe, and maybe share it with a few friends. Okay, now that we understand what degenerate matter is and what non-degenerate matter is, let's take a look at some thermodynamic properties of degenerate matter. So we're going to take the t equals 0 limit. So now our probability distribution is 1 if the momentum is less than the Fermi momentum, or the energy is less than the Fermi energy, either way, and it's 0 otherwise. We already found what the number density looks like in this case, and this integral is fairly simple to evaluate. What's important to take away from this result is that for degenerate matter, the density will be proportional to the Fermi momentum cubed. Here I've replaced the number density with the mass density rho, but the mass density and the number density are related to one another. And again, remember that the Fermi energy and the Fermi momentum are related through this standard energy-momentum relationship. In Stellar Physics 2a, I derived a general form for the pressure, which will reduce in the degenerate case. This integral is a little more difficult to integrate, but it is solvable. Here I've done a convenient change of variables. X is the Fermi momentum divided by the mass of the particle times speed of light. This is a dimensionless quantity and is often referred to as the relativity parameter, because if x is large, then you're relativistic, meaning the momentum is much larger than the mass, and if x is small, then you're in a non-relativistic regime because the mass is much larger than the momentum. This term h bar divided by mc is called the Compton wavelength, so it has units of length. And I'm going to write this entire expression as the mass divided by the wavelength cubed times this function f sub p of x. Using similar notation, I can rewrite the number density as 1 over the wavelength cubed times fn of x. In this case, fn of x is very simple. It's just x cubed divided by 6 pi squared. In Stellar Physics 2a, I also derived a general expression for the energy density, which we can also reduce in the t equals 0 limit. And again, this integral is a little bit more complicated to evaluate, but it can be done. And I'm also going to rewrite this as the mass divided by the wavelength cubed times some function fu of x. Now, this energy density includes the rest mass energy. And typically, what we want is the internal energy, which is defined excluding the rest mass energy. So epsilon here will be the internal energy per unit mass, which I get by taking the energy per unit volume, dividing by the density. And then I've subtracted off the rest mass energy density, because we don't include that in the internal energy. Now I want to look at what happens in relativistic versus non-relativistic regimes. Let's start off with relativistic degenerate matter. So we're going to take x, the relativity parameter, to be much greater than 1, meaning the momentum is much greater than the mass. The number density is the same whether it's relativistic or non-relativistic. And I'm going to replace the number density with the density, meaning the mass density, which gives me an expression for x in terms of the density. So x is proportional to the density to the 1/3, which we found on the previous board. For the pressure, we can Taylor expand Fp of x in the case where x is large, to find that to first order, the pressure will be proportional to rho to the 4/3, where 4/3 is the relativistic adiabatic index, and k is a constant. And here I've included the first order correction term as well. We can do the same thing for the energy density. To get that to first order, the energy density is 3 times the pressure, which is the standard result for relativistic matter. And again, I've included the first order correction as well. Now let's take a look at non-relativistic degenerate matter. This time I'm taking the relativity parameter to be very small. The number density doesn't change. It's the same whether it's relativistic or non-relativistic. The pressure in this case, we expand assuming that x is small, and we find that it's consistent with what we found in previous videos in this series. The adiabatic index for non-relativistic matter is 5/3. And once again, I've included the first order correction term. We can do the same thing for the energy density. And here notice that I've included 2 correction terms. And the reason for this is that if I plug in what x is in terms of the density, this first term will simply be the rest mass density. And ultimately, we subtract off the rest mass density. So actually, the first order term will be this term here, and this will be the next correction term. Okay, so now we've covered the number density, the pressure, and the energy density. The only thing left is the entropy. Well, we know that if the temperature is 0, the entropy is also 0. From the first law of thermodynamics, we have this expression for the entropy in units of K-Boltzmann. I prefer to divide the entropy by units of K-Boltzmann because that makes it a dimensionless number, and it's always nice to have a result that doesn't depend on dimensions. So as I said, this is taken from the first law of thermodynamics, which is usually written as U equals a bunch of stuff. I've just rearranged it to solve for S. Now, since this has to be 0 at t equals 0, this implies the following equation has to equal 0. So all this is the sum of the energy plus the pressure plus the Fermi energy times the number density. And this term here results from multiplying by the Fermi energy, where the Fermi energy in terms of x will look like this. Remember that x is basically a proxy for the Fermi momentum. And sure enough, if you plug in f sub u, f sub p, f sub n into this equation, you will get 0. I'm not going to do it, but I encourage you to check for yourself. So if we want to know the first order entropy term, we can't take t to be exactly 0. We have to include the first correction at t is close to 0. So in order to do this, we're going to use what's called the Sommerfeld expansion. This is just a mathematical trick for approximating an integral of this form, assuming that this term eta in here is large. So if you have a general function h of z that's divided by this expression here, integrated from 0 to infinity, that will be approximately this integral here, where the denominator is 1, plus this correction term, involving the first derivative of h of z evaluated at eta. So let's plug this into the pressure. This integral will be P naught, which is the pressure at 0 temperature. We already know what that is. And then this term here will be the correction term. We can do the same thing for the energy density and for the number density as well. Now we plug all this into our expression for the entropy, knowing ahead of time that P naught plus U naught plus N naught times this factor will come out to 0. And so all that will be left will be these correction terms to get the following expression for the entropy at very low temperature. So we can see that if the temperature is exactly 0, the entropy will also be 0, so that's a good sanity check. If we're in a relativistic limit, then x squared will be much greater than 1, so this whole thing will be proportional to x squared. And in a non-relativistic limit, 1 will be much greater than x squared, so we can ignore it, and this will be proportional to x. And remember that x is proportional to the density to the 1/3. So what we've done here, if we go back to our visualization of degenerate matter, at t equals 0, we're here, the entropy is 0. And we just found what the entropy is if you're at t is close to 0. So the entropy we just calculated accounts for these particles up here that have a little extra energy above the Fermi energy. Okay, now you know everything there is to know about degenerate matter. That wasn't so bad, was it? We're now going to take these results and apply them to degenerate stellar cores, starting with the Chandrasekhar limit, which is the maximum mass of a white dwarf. So if you enjoyed this video and would like to see more, be sure to like, subscribe, and hit the notification bell if you haven't already, so that you can be notified when this video is released.